Welcome to the session. I'm Sander van den Ban. I'm the Technical Development Manager at Elmac. I'm responsible for formulation and manufacturing process development, manufacturing support and capital projects. The presentation here is based on an article published in the International Journal of Pharmaceutics titled "A Real-Time Release Testing of Tablet Content and Content Uniformity." I must stress straight away that any view or opinion that I make here is that of my own and must not be attributed to Elmac, directors, officers, employees, volunteers, members, chapters, councils, communities or affiliates or any other organization which I am employed or affiliated. Now, the context of the current work is that within QBD, obviously, we consider a manufacturing process well understood when it meets the product quality attributes consistently. We understand sources of variation, we can detect, control, and monitor them. Within the industry, there are a large number of applications of NIR that you can find published to monitor content or content uniformity, but more often than not, they're focused on the method itself and not necessarily the application like regulators expect you to do. And as such, what we've done is in this presentation is try and see if we can get a control strategy that provides the right level of protection for the patient in terms of quality, and what we would need to do statistically to prove that for the entire batch, and how we may be able to use this as a real-time release and what its limitations are with the technology we employed. And as such, you need to take a wider view basically of how NIR is an element of the control strategy rather than the control strategy itself. So within that, either QBD or guidance documents, actually, it's quite a complex picture in that there are plentiful guidance documents out there for NIR alone, whether that's the development of the method or validating them or indeed maintaining them during the life cycle. And only when you deliver all components together will this work. So for us, I have spent less time on the NIR method itself. I have attached a slide at the end where it demonstrates some aspects of the specifics of the NIR method. I will not go into detail during this presentation, but rest assured that we challenged this method both by exposing it to variation of tablets themselves, weight, thickness, hardness over the full range of IPC limits and beyond, as well as content between 75% and 125%. And there's some data, and again, you can find that data in that article published online. Again, the more important thing is how can we apply it in a totality. Now, one of those things is when you check QBD, this is from another industry, and generally speaking, the chemical industry, where they use something called layer of protection analysis, and the diagram you see is called a risk bow tie because it looks like a little bow tie that a person might wear. So not only is the focus on identifying the risk and trying to detect it, and more often than not, QBD tends to be focused on identifying that risk and try to prevent it. It also works on the premise that you know, should the risk materialize, what will you then do to mitigate against it? Now, although this sounds fairly complex, you're probably used to this in your own life already, right? So if you look at the risk of fire, there'll be a number of protections made, whether they are in an office, for example, to reduce quantities of flammable materials or implement fire doors. You will also know that should the fire be there, alarms will generally go off and you'll probably have to go to an assembly point. So some mitigation of should the risk have materialized. Now, Those control strategies are seen as better when each of those controls you do is independent, so one does not impact the other. You can rely on them, you can check them individually, and they're very specific towards preventing that risk from happening. And as such, if you have a number of elements, it will see that as stronger. Should you want to read up some more, it's a similar model, for example, that they use when you travel to prevent people with malintentions from entering a flight. Apparently, there are 17 independent layers of control. Now, if we check out risk to uniformity based on uniformity of dosage units like they are stated in the harmonized European, American, and Japanese pharmacopoeia, there's generally speaking two elements, content uniformity and mass variation. So some of the risks that we would be concerned about is the mixture becoming non-uniform through segregation, of which obviously there's multiple types. Generally speaking, even within that pharmacopoeia, it states that in essence you could consider the risk less if the dose is more than 25 milligrams and more than 25% in concentration, with a special case being ordered mixtures with a low relative standard deviation. You can test that. So there's some approaches. I've given one here called the Elkowski equation, or indeed testing segregation potential of powder that you're intending to compress. That risk typically happens at batch startup, batch end, and when you stop and start, and that is when I think when you're sampling, which is the direct link, you must be able to detect those type of issues. Now, similarly, from a weight variation perspective, we're obviously concerned about powder flow, so we want predictable, good flowing powder such that each and every tablet will have a narrow weight in control of specification. Generally speaking, although there are a number of measurements, whether they are angle of repose, bulk and tap density, shear cell tests, etc., from an industry perspective, compressibility index is the most straightforward to apply and reasonably predictive. If you have a karst index less than 30%, it tends to flow well. If it's more than 30, it tends not to, according to the criteria stated, which meet those that we see in industry and in practical reality. So again, you would see this generally at batch end. I think when the hopper height gets low, that little bit of pressure to make sure the dies get properly filled does no longer exist, and you probably get weight issues at end of batch. You need to decide when to stop. And similarly at start stoppages, sometimes that might lead to issues with weight control, particularly where the press has been stopped for an amount of time, for example, when you got a strongly consolidating powder. So from a risk mitigation, what we're interested in is to design the product and the process. One such way of doing that is comparing it to manufacturability criteria, which would indicate the likelihood that you get a high quality product coming out the other end. In this particular application, the actual drug product that we intended to design has got a dose greater than 25 milligram. It's 160, and it's also in a concentration exceeding that of 25%. Its core weight was 400 milligram. We had micronized the drug, and the drug product is granulated, which again would provide acceptable powder flow. Now, some of the other elements of control that you might want to do is, and we'll get to that it's important that we make a statement of quality for the entire batch, that the sampling plan can pick up on that. And as I said, some of these might also actually lead to the need to, in some instances, what happens in industry is that you have to discard part of your batch at the start or indeed at the end when you can no longer get the correct weight done. So that's what we'll be going through. Now, there's two elements, generally speaking. So element one is a control that already exists, which is on the tablet press itself. I've highlighted the compression triangle you may be familiar with, which is the picture on the top right. And I can even highlight that, which is this triangle, which is generally what happens on the press. So on the press, if you've got good powder flow, which allows you to meter accurately at commercial relevant speeds. So typically commercial presses can run between 1 and 6,000 tablets per minute, which gives you very little time to fill each die to a high precision. We would then compress that unit. The punch spacing is directly proportional to the thickness that you get. As a consequence, you create a tablet of strength. And that force that we measure to compress that tablet can be used in compression loops. So the way the machine works in commercial setup where this technology is available is it compresses them to a constant volume. In that instance, weight and the force you record to do that are linked. So more weight in the same volume would generally result in a higher force, and vice versa. A lower weight in the same volume will result in a lower force, and as such the two are directly linked. What it allows us to do then is to use the force in a control loop to control the weight of each and every tablet. Generally speaking, there's 2 loops in operation. For some presses, there's more than 2 loops. One loop to control the weight. What it does is it compares the force measured corresponding to your target weight, and should you be slightly over or under, it adjusts the fill depth or dosing depth, which is the column of powder you take to compress, such that you return the press to that target weight. So that allows you to control the target. And the other one, if that force corresponds to a tablet that's grossly over or underweight, there is a mechanism whereby it can eject that tablet off the press. So it's called a fast gate. It tends to blow them off, typically more than 1 tablet because of the speed that they run at, but it would remove and segregate that product from good product. Now, one thing you do need to obviously monitor is for products that are lubrication sensitive, obviously that loop may be impacted, and similarly press speed is theoretically a CPP because the time that it takes to fill the die is impacted by the speed that you manufacture at. So you might have to check that that loop is not speed sensitive. This is an example of how you can get the compression force reject limits. We exploit that triangle while making tablets of various weights and thicknesses and measure the braking force and the resulting main compaction force. Within the manual, there's a little way of how you can manipulate the data to re-put the weight relative to the target and then recompute that compaction force relative to the target, which gives you this line. We did this at thicknesses exceeding the IPC limits, 4.7, 4.9, and 5.1 millimeters, recorded their variation in weight, and recorded their variation in the standard deviation of that force and got a correlation out that way. Now that means that if the press records a value, in our case we set them slightly tighter at 3% of the weight target, based on pharmaceutical limits for weight. Basically, it says that if you hit this particular weight here, it would be a tablet that's overweight, or if you hit that relative deviation in force, you would have a tablet that's underweight. That allows us to dial that up on the machine, and then all is good. One thing to mind, and I won't go through this in detail, you can get this from the manual, but is that our ability to set the weight absolutely the same every single time is impacted to do so. So you do get minor variation in compression properties batch to batch, which would mean that that value tends to be set up on each and every batch. It won't vary much over its life cycle, but it will vary batch to batch. But there's a zone where the press actually does absolutely nothing, which is called a dead or a gray zone, typically relating to about 1%, which crudely speaking is the equivalent of 0.5% of weight. So even if you set it up, the press will not respond within a tiny weight, and that causes variation in itself. Similarly, I think things to consider are that the weight or the way the force is being computed depends on what the press is. So more often than not, it's the average of 2 rotations that's updated every other rotation, and that again dictates how it would impact the performance. Similarly speaking, for individual weights, this is how the press does it. Typically in practice, you set the limits a lot tighter on individual weight than you have to, both because the way we determine the loop is based on means, whereas obviously it rejects individual tablets. That's because the speed of the press is so fast, we cannot correlate one individual force with one individual tablet. Again, they're coming off at the rate of about 50 a second in our occasion. We just simply cannot match them. You need to determine during running that you actually have the weight within. So you need to set the limit slightly tighter, otherwise you cannot determine whether they're truly in or not. So again, there's a fair amount that you need to understand from the press to get this correct. Now, here's the actual data that we got. So you can see with the little blocks representing the mean, you can see what the variation in the mean was that we had. We've done this both at 140 and 180,000 tablets per hour. These are commercially sized batches, each batch being 330 kilos. And you see the arrow bars represent the min and the max. So as you can see, we got our tablets to individual tablet weight to plus or minus 3% based on the sampling that we did, which is approximately 10 IPC tests for a batch sampling 20 tablets. So this total of 30 batches represents about 6,000 tablets sampled. Now we also got them at high yield, so very little tablets were actually ejected, meaning that we get good control over fill weight in itself. Now, if we then shift towards content uniformity, the actual NAR tablets, typically what gets done for content is we take 10 tablets, we perform a bulk assay of 5 tablets in duplicate, average them and report them. There's a slight difference between reporting in the EU and the US based on local requirements. For content uniformity, we follow the USP or the EP, but crude or really important here to state is, although the test might look statistical, they are not a statistical statement of the quality of the batch. It's purely a result for those tablets that you test. So you don't actually know what the quality is of all the other tablets that you have not tested, nor can you make a statement. So the US in particular has made quite a key point here that states that you must make a statement of the quality of the batch, including those batches that you haven't tested and what the likelihood is that those tablets will pass if you did. So in their book, if they were to randomly walk into a pharmacy where that particular product is sold, they expect it to comply, and if it doesn't, you have adulterated the product. So what they're looking for is what's the quality of the tablets that you didn't test. Now, that's perfect for applying some NAR, which hopefully means that we can fastly test some tablets. So what we tried and do, so we obviously developed an NAR method. So there's a couple of methods of how you could do that. Now, one that's published is a Bergen method, which is one option, which we didn't actually use because that method is geared towards confirming the likelihood that you pass the EP test. So again, in what I just described, that is not what we were looking for. We were looking for a statement for the overall quality of the batch. So options we have under uniformity of dosage units, we can just do it by weight. But obviously you still have that risk that tablets are not at the correct concentration of active and therefore you would fail. So it's an inbuilt assumption. We can do it from estimated tablet content data, but that doesn't allow you to use the PTI toast statement because the statistical properties are no longer valid if you compute it. So what we did is we went by the individual tablet content by NAR. Now, we measured 50 tablets by batch. I'll tell you some more about how we got there. So statement of quality for the batch could look something like that. With 95% confidence, we can state that at least 87.5% is covered within the interval of 85 to 115% of label claim. So the bits that we haven't covered in that means that 6.25% either side have tablets that have a content no greater than 85 or 115 or above. And there's a zero tolerance criteria involved in the large sample size chapter from the European Pharmacopoeia, which is 2947. Now, this is what that criteria looks visually. So we're expecting less than 6.25% of tablets to have a quantity greater than 115. Similarly, less than 85% and 87.5% to fit within 85 to 115. Now, mathematically, it ends up being rather a simple representation in that it literally is this formula here, which ends up being a triangle. So in essence, the further away from target you manufacture, the tighter standard deviation is required for the product to pass. So it rewards you for manufacturing to target, and the further away from target you get, the better you need to be at control and content uniformity. So fairly straightforward formula. In our case, these values are published, this little K value, so it's average minus or plus the K value times your standard deviation. And in our case, that value is 194 in a first, just a one-tier model. Now, some of the things we did was just check the statistical properties. So first thing we did is that's actually very hard. We taken 5 tablets simply because it matched a content uniformity test, in which case each IPC would be a content uniformity test. The problems we had is it actually takes 20 seconds to take a spectrum per tablet, but the press runs at 3,000 tablets per minute. So that in itself limits you quite dramatically in what you can do. It also meant you have to have a separate system to take the tablets, transfer them, and then maneuver and analyze them, because you can't keep up. Now, what we did do, these are statistical curves, which tells you the probability of accepting a good batch. In short, basically, it tells you that 10 tests of 5 tablets each, which is marked down here, gives you a very good statistical performance, and an increase in the number of tests doesn't necessarily lead in any greater ability to detect whether the batch will pass or not, and hence we stayed with 10 tests, which allowed us a half-hour IPC interval, which is sufficient to be able to do the test and potentially repeat it again, in which case, in case you got issues with sample positioning, etc. So it took us 12 minutes to take an IPC test. It allowed us for a one-fold redundancy within that 30-minute time period. Similarly, we compared the statistical performance against just performing weight alone for whether we were at target or not at target, which is what these 4 graphs display. In each instance, the power of the PTI toast is better and more discriminatory of quality than the uniformity of dosage units. Now that brings us to a control strategy if you bring it all together. So in terms of the LOPA technique that I discussed. So in our case, our press speed was purely limited by the press, is in that the manufacturer tells you to not run any faster to prevent an increased rate of wear and tear. That's why we limited to 180,000 tablets per hour. We could actually run faster. We apply compression limits that are stated as 15% of target, which will help us control over and underweight tablets. Independently, we take IPC tests, both for mean and individual weight. And in addition, we apply a content measurement by NIR of the mean of 5 tablets on each IPC to this quality statement. So again, that would make it a comprehensive control strategy. And obviously the protection level that we provide with this control strategy is our quality statement. So overall, as a reflection, this quality statement that we've given is valid for the entire batch, and as such, we've met the USP requirement that they state in that we must ensure that the batch is uniform, not just the tablets that we tested. If you compare how many tablets would normally be submitted at level 1 testing traditionally by HPLC, it is 10, so now we would test 50. Over time, we got better at doing it with the device, and we could probably go to 100, which would represent an order of magnitude increase. That number of tablets is sufficient to demonstrate the quality. Now in industry, we also have to provide an identification test on release, which is the exact same HPLC method that we use for content. So for us to gain an operational benefit and a cost reduction at the same time, we would have to also get a real-time release method for identification. Otherwise, the analyst will still have to use that HPLC and do that intensive work. Now, the other one is where we apply the NAR. Actually, at that point, we cannot change the quality. So possibly in a continuous manufacturing process, you could imagine that that's fed back to some ratio control of ingredients. But actually in a batch process, what this was used for, it can only detect and potentially segregate, but it can certainly not apply an automated control. Now, this is the performance of the actual control strategy. When we put it all together, we performed 10 batches in a row with it all working. You can see from the data that both the weight well into specification, so the NIR, and we matched that up with end product test, and I can tell you that the two methods were equivalent. So again, very effective control strategy. Obviously, unfortunately, we cannot ask any questions, but we can do in the question and answering session that we've got scheduled, I believe, later in the day. So thank you for your time, and we'll have questions soon.